This video is for the fabulous Miss Hoggett and her class, who I briefly met the other day, as well as all my usual students. Have you ever noticed the crash barriers along the edge of the motorway? Well, if a vehicle crashes into the barrier folds and bends and moves, and so does the vehicle that hit it. If two vehicles were travelling at the same speed and they hit a crash barrier, it would make a big difference to how much damage was done if the mass of the vehicles were different. If the same vehicle hit a barrier at a faster speed in the same direction, a higher velocity, that would also make a big difference. And you've guessed it, this is all because of momentum. Moving objects have momentum, and it can be calculated by multiplying the mass in kilograms with the velocity in meters per second. The momentum would then be measured in a unit called the kilogram metre per second. So the crash barrier stops a vehicle going any further by removing its momentum, and it does this by gaining the momentum from the vehicle in the collision. The force of an impact can be calculated because it depends on the rate of change of momentum. It depends on the amount of momentum that's being reduced down to zero and the time it takes to change that momentum. So the longer you can make a crash last, in terms of how long it takes to change the momentum to zero, the lower the force will be. If you're in a car that's moving, your body is going at the same speed as the car. When the car stops suddenly, your momentum continues to take you forwards. Your seatbelt is designed to stop you hitting the steering wheel, the dashboard or the windscreen. It does this by stretching, and the time it takes to stretch reduces the impact force on you because it's reduced the rate of change of momentum. Crumple zones are specially designed to squash and fold to help the momentum change to zero over a longer period of time. This reduces the force on the driver and passengers. And another safety feature are airbags. These inflate by a canister of gas and have little holes in them to let that gas out as your head hits them, increasing the time it takes for your head to come to rest. Tom's going to help me try a quick experiment that you could try at home too. Okay, so Tom is going to try and drop this egg from a really low height and see if it breaks. Go. Is it broken?
No.
Okay, so try it a little bit higher.
Ready?
Yeah.
Yay.
And a bit higher.
Mm-hmm.
Oh, that didn't sound good. Is it broke?
It has a little crack in it.
Oh, not a proper... Oh, I think we should do it a bit higher then, don't you?
Yeah.
What do you reckon?
Ooh.
Drop it from the other side now.
The what?
Drop it from the other side. Hold the crack bit on the top.
Ooh. It's so yucky.
Yeah, just see a bit higher how much it mangles it. Go on. Yeah, alright, that's pretty mangled. Cool. So, now we are set up for phase 2. We have an egg of very similar mass, because it came from the same packet. Still got our 2 sheets of newspaper, cleaner newspaper than the eggy one. We've got some bubble wrap, a tea towel, and a doormat, all helping to create our crumple zone. So squish that bubble wrap back up a bit, darling. That's it. Put the newspaper on top. And I would like you first to drop the egg, not as low as we did the first one. I want you to go to where it cracked the first time. Not as high as where it mangled, where it cracked. So what you were doing is 3. Is that about there, was it? Go on and see if it cracks this time then. Did it crack? No crack at all. Okay, go up to your position for mangling the first egg and see if we get a crack from that. You see, this is a really scientific experiment with our heights here, but that was pretty convincingly not broken from the same sort of height. Okay, but don't go too high too quick. You're going to 6. That's your version of 6, is it? Okay, let's go for it then. Is it broken?
No.
Oh, you might have to go a bit higher, mightn't you? I want you to break the egg.
7.
I need to show how high this is getting now in front of our beams. Right, go on then. Yay, there you go. Alright, drop it from the other end then. You're just trying to make my kitchen absolutely covered in egg, aren't you?
Right, time for 9.
Right, I'm filming from up high. Go. That's it. That's the end. Stop. So the two eggs had equal mass. When dropped from the same height, they accelerate in the same way because their weight is greater than air resistance. So just before they hit the ground, they have velocity and mass. They have momentum. Once on the ground and stationary, the egg has no momentum. Are you wondering where it went? Well, that's the floor, but more about that later with some balls. So, if momentum is mass times velocity, before it was the same from the same height, the crumple zone we created, or the airbag really I guess, squashed and moved to increase the time it took to change that momentum to zero. So with the materials in place, the force was reduced enough to prevent the egg cracking. Tom had to increase the height quite considerably to get the egg moving fast enough to have more momentum so that for the crash taking the same amount of time, it produced enough force to crack the egg. So we've thought about changing momentum and how it affects the force on a collision. We've also talked about how to calculate momentum by doing our mass times velocity equation. But it's really important to also consider that momentum is a vector quantity. It doesn't just have a magnitude in kilogram meters per second, a size, it also has a direction, and direction really matters in collision problems. We usually take forwards to be a positive momentum, and backwards is shown by using a negative sign. Momentum is conserved. By this I mean that when two objects collide, their total momentum remains constant, as long as there's no external forces acting. So, the total momentum of a vehicle that crashes into a crash barrier is equal to the total momentum of the barrier and the car together after the collision. The barrier moves, folds and bends along with the vehicle. Through the rest of this video we'll use some examples, so let's start by looking at my Newton's Cradle. Here there are 4 stationary balls and 1 moving mass. You can see the momentum is conserved because the ball at the other end with the same mass gains the momentum and so on. When I double the mass at the start here, you have more momentum, and so 2 balls move at the other end to conserve that momentum. And here, 2 moving objects are colliding from opposite directions, but you can see that momentum is still conserved. The Newton's Cradle provides a pretty near elastic collision. In an elastic collision, all the kinetic energy is transferred into kinetic energy. A 100% elastic collision would not waste any kinetic energy at all as thermal energy, heat or sound. In inelastic collisions, the kinetic energy is not conserved. It is transferred to thermal energy and sound. Both elastic and inelastic collisions obey the conservation of momentum though. In both elastic collisions and inelastic collisions, the total momentum before the collision is equal to the total momentum after the collision. Let's have a look at that idea with Tom and his selection of balls. Tom dropped 3 balls from the same height. Notice his large mass football hardly bounced back at all. His mid-mass mini basketball rebounded about half the way back up. And the tiny ball, nothing, no rebound at all. These were inelastic collisions. Each ball accelerated down, transferring gravitational potential energy to kinetic energy. Its mass was travelling at its fastest just as it collided with the floor, so they all had momentum because they all had mass and velocity. So there is momentum before the collision, and there is momentum after the collision. You can see some in the rebounding balls, some momentum in the opposite direction after the collision. But the rest, well, the floor has momentum. It's a massive, and it compresses as the ball collides, moving it just a tiny bit. It might be more obvious to see in Tom's next demonstration. So with the largest mass below the middle mass, we see the momentum conservation causing the large mass to stop dead and the middle mass to move off at a faster speed. And with the tiny ball, you'll see that speed again because of the conservation of momentum. There's a good little simulation if you go to this website. You can have a try. So on this simulation, you can get objects colliding and you can highlight values for the collision. You can change the masses. You can also try things like changing whether it's an inelastic or an elastic collision. It'll give you a chance to have a play around and a practice with some of the calculations in a bit more of an interactive way. So why not give it a try? If you've been in a lesson with me, you'll probably remember this. Can you remember what's wrong with it or work it out? And here's the right answer. Direction is so important. Why not try the advanced version of the simulation to have an experiment around with two moving objects? Add momentums or take them away. Let's recap with these three examples. So in A, the white ball has zero momentum because it's stationary. The orange ball has a positive momentum from its mass times velocity. After the collision, the momentum from the orange ball has been transferred to the white ball. The white ball now has a positive momentum. It moves off at the same speed the orange ball had been because they're the same mass. The orange ball has stopped, it's stationary and has no momentum. In example B, we have a head-on collision with two objects of the same mass moving together at the same speed. So the total momentum before the collision is zero because the orange ball's positive momentum is equal to the white ball's negative momentum. The balls move away at the same speed and in opposite directions, so after the momentum total is zero as well. Momentum is conserved. And our final example C shows the faster orange ball hitting the slower white ball. In the collision, the orange ball slows down and the white ball speeds up. And that's all because momentum is conserved. Let's finish with a couple of applications for our triple students. In an electron-positron annihilation, momentum is conserved. The two particles have the same mass and are moving at the same speed in opposite directions. They have momentum that's equal to each other in magnitude, but opposite in direction. So one positive momentum, one negative momentum, means the total momentum before is zero. The two gamma rays or photons that are created as the mass becomes energy move off in opposite directions with no mass. And so the total momentum after is still zero. Momentum is conserved. In the Large Hadron Collider, accelerated protons collide with accelerated protons, and the detectors that are at Atlas and CMS will be measuring lots of things, including the momentum before and after these collisions. This helps them to identify what particles have been made in the collision and will help answer questions about things like dark matter. I do hope this video was useful. It ended up much longer than I'd first intended it to be. But remember, this revision is helping because you know that
Regular review gets a better grade for you.
Don't forget to
Like,
so that I can keep making the videos.
comment,
Especially to request other revision topics.
subscribe.
So you can get notifications of when my next video gets uploaded.